Hello, 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 oh,
Morning.
hello, Kimberly. Thank you. Hello, Andre. Hello, Amber. Hello, Wen Yi.
Hello.
Hello. This is not. I'm just saying hello. Hello, Rachel. Hello, Armand. Hello, Sharon, whose name I still am not pronouncing correctly. Hello, Marissa. Hello, Jenna. Hello, Aaron. This is my new thing. Isn't it cheesy? Hello, everyone. Who else? Good morning. Yes, thank you. Good. Hello, Yaobo. And again, please do start correcting my pronunciation as I'm getting. Hello, Sarah. Hello, I have no logging from another device here. I don't even know what that means. Okay. Hello. Oh, and the thingy. Um, hello. Who's that? Hello. Okay. There. Okay. Before, so what it says on the board is SHO. I don't know if I use this word yet or not. SHO with like the topic of today. Oh, hello, Wendy. Hello. We're still in sheet one here. We're still in homework one. Like we'll address administrative and grading stuff in a minute, but the context is still a thing on a spring. But I'm going to start introducing. Good afternoon. Good to see you. I'm going to start introducing the term harmonic oscillation today, like if I didn't already. SHO, like it says on the board, stands for simple harmonic oscillation. In fact, let me give you before I forget. That's our topic. That's the what we're really getting into here. 1 second. Sorry. Um, okay. Um, and hello. I'm just going to good afternoon. Oh, good afternoon. Um, okay. So we're going to get, momentarily, we'll get back to that sheet of homework one, the thing on the spring, and keep doing it. Like we're starting to get into some physics here. Yeah, I think we really did start getting into physics last time, but just administratively, so a couple of things. Number one, as far as a game, I'm still trying every day to make this a little clearer to everybody, the whole a game thing, the class participation points. Um, but each time I try to make it clearer, I may be confusing people. So I renumbered things and stuff and tried to clean it up a little bit on your end. But then I shifted deadlines around, so it might be scary to some people. And again, with the game thing, it's all optional, and any deadlines that I'm putting in there are just to help you track it and organize it more. But I'll accept those at any time in any space, the game things. But just to sort of understand them better, my theory is that we were all in class together on the very first class, like last Monday, class number one, right? We were all together. And in that class, I asked you to do your first sample of that a game thing, and you all did. So you all got 50 points for that day before the class was even over. Or, I mean, you submitted it. Um, so I'm going to keep it out. So I retrospectively call that turn one. Okay. Then the next class is turn two. And you'll notice weirdly, like retroly, I'm just saying we can continue that model and say, in theory, a half hour after class is over, like in theory, we shut down class, and then before you go on to your next class or whatever, take 5 minutes before you forget to jot down the thing. So in theory, I'm saying at the end of a class, for every class, the turn for that class is due in a half hour. Again, I don't care if you're late with it. It's not about, but it's just to make the numbering and everything easy. Class one was turn one. It was due at the end of that class, half hour after that class. Class two was turn two. It was due a half hour after that class. Turn three was 2 days ago, Monday. In theory, and again, I all retroed this. So, but turn three was due a half hour after that class. Today is our fourth class. Turn four is in theory due a half hour after this class. Again, of course, tonight you can go back and fill in the one from Monday, and you can fill in the one for whatever. Nothing is late or anything like that. But just hopefully this will just keep it clear from now on that, like at the end of every day, there's a turn for you to submit your 50 points. They're all the same. Then any one of these game assignments that's popping in that doesn't have a number, like you already have one that's called your best, and I hope I explained that. I'm happy to explain it again if anybody asks. but then you have one that's for right or for wrong. Note they both don't have a number, and at least one of them is worth 75 points rather than 50. Then today I put one in your box, also reminiscent of last semester, the one that's called like Speak Now or Forever, Hold Your Something Something. And that's for an extra reward if you ever or whenever you use your voice. Again, you can double and triple dip, right? Like again, at the end of today, if someone used their voice today, at the end of today, they could make a note of that in turn 4, turn it in for 50 points, but they could also turn it in that voice portal that's technically due at the end of the semester and get 75 points for that same entry. And I'll put more of those voice, and you can use one more than once too, if you want to, whatever. But that's how that's supposed to be working, that the numbers are just like one for the first class, second for the second class, and then any non-numbered ones are just whenever you want to fill them out. That's that. Homework wise, I believe at this point.
Sorry, I'm having trouble hearing you.
Oh my God. Okay. Sorry. Did you guys hear that? I just got interrupted by Siri. I really enjoy being interrupted by Siri. What I enjoy best though is when I get in the car and I literally have to tell Siri to deploy Mrs. Google because I like Mrs. Google better. But I have to get Siri to like give me like joint custody over our child and like anyway, well, yes, that is true. All right, fair enough. But if Mrs. Google is the government, then Siri is like the devil in the deep blue sea. I mean, Siri is even more insidious, I think, but I don't know. What the? So sorry, that was Siri. In fact, I'm going to put Siri in her place. Excuse me. Nobody puts baby in a corner, but people put Siri in a corner of my house. Can anybody name the movie, by the way, for 25 points? Name the movie. Oh God.
Dirty Dancing.
Nice. Wow. Yes. Awesome. And thank you for one moment. I was so worried that I just made a reference that made me seem like that guy. Yes. Dirty Dancing. Awesome. Okay. Excellent. I think it was you guys that taught me that expression, I'm dead. I still can't even get over that that's a thing, but I can't get over that it's a thing is a thing, by the way. Like a thing was not a thing until like your generation, but it's great. Your homeworks. So thing on a spring, I'm pretty sure pretty much everybody handed in. And again, if you didn't, there's still time, but I think everybody did. I think most of you got it back, which is great. The one thing I'll just say is please remember to circle your answers. And especially if I keep up with your homework the way you're keeping up so far with me, like really get in the habit of circling your answer, especially when you're really insecure that it's wrong. The more you're worried that your answer might not be right, actually, the more you should highlight it, especially to test me and to test whether I'm really going to make good on my promise that it is all about the answer, but it's not all about a right answer. If you see that subtlety, like by circling your answer, you're showing that you actually know what the question is and what type of answer it's looking for. That's so important in science, so much more important than getting the answer right, especially if that's going to hold you back from actually publicizing your answer. So anyway, circle your answers. So everybody did great on homework 1. A lot of people handed in homework 2. I'm very aware of that. I've not started looking at it yet. I apologize. But I think technically that was another thing. I know I talked last time, you don't have to do the dot cross product part, blah, and that's still all true. But I hope you'll find that I think I retweaked it so that, or maybe you should tell me. I think I changed it so that the math methods homework assignment, I think I shifted it so that it's actually due next week, which means next Wednesday because we don't have school Monday. Is that right? First of all, chat.
Oh yeah, that's right.
Thank you. Okay. English is fake, but that is right. Okay. So good. So it's not again, if you've already turned it in, I'm aware of that. I have it. Like you're getting credit. Your Lord knows that you are that responsible, especially if it caused you any stress to try it for it's clear that you did it if you did it. But if you haven't done it, there's no harm, no foul. Yeah, it's due next Wednesday. But let's say by that point, I want you to try, even if I don't get to talking about them, try the whole thing by next Wednesday, because it is a while. Even the part about dot and cross product, anything. And from here on, this is true for all of you. Let me say, we're going to do some math in this class. There's going to be a lot more calculus than there was in physics 1. That is the reality. Anytime we do calculus here, it's because we need it and want it and love it, or that I love it. It is not between you and me. I know you all have all these calculus prerequisites to take this class. When we do calculus, I'm not doing it with the assumption that you've already mastered it. Any calculus I do, I'm thinking I'm I'm referring to things that you've seen before, so you like know kind of where they fit in the world. But I'm thinking that we're actually using physics to teach ourselves calculus. That's how it worked for me anyway. Secretly, I believe physics should be a prereq for calc, not the other way around, or at least for a lot of people. Either way, please know that the more and we're going to get into calculus here, just know at all times, I think we're trying to learn it together. So you're allowed to ask questions and stuff. I'm not assuming that you got it just because you did it. And even if you did it really well. That said, please do try the math methods homework for next Wednesday, because even parts like dot and cross, I'm not assuming that you know. I'm assuming that I'm giving you enough there to work with, that what you just need are the definitions and take them seriously. Okay, we'll try to get to it anyway. But anyway, that's that. So I think that's administrative things. We decided on the midterm here, I believe, right? So I believe I want to just dive back. It's not too okay. So I want to go back to where we were in the middle of the thing on the spring, if that's okay. In fact, where I think, and you're gonna have to remind me, but I believe we're up to question 6. Maybe someone tell me in.
Yes, we're on question 6.
Sorry.
Yes, we're on question 6.
Great, thank you, perfect. All right, so okay, so that's where, so I'm gonna do that. Yeah, that's where we're going here. And again, also, you guys, a lot of you know me well. Please, if I start, please interrupt. If I just start going off on something, like please, or tell me to skip ahead if I'm going too slow. Like, I hope you're comfortable enough to do that. But here we go. So it was 6. All right, so 5 was the thing. Okay, so if we did 5, we beat to a horse, we beat the dead horse of that energy conservation, all that. Now suddenly we take a little departure, if I recall. And the next couple of questions are almost more relaxing for many of us. They're less mathy, but they are, and they might even seem obvious to some of us, but they're super important to set up something. So if I recall correctly, number 6 was the one, where's the next time we'll find the mass? The next time we find the mass with an instantaneous speed of 0. Am I correct that that's the question for number 6? Or does someone want to?
How far will the mass compress the spring once the mass has, instantaneously stopped and is about to reverse direction?
Great, perfect, thank you. And that was that's you, Kimberly, right?
Yes.
Great, awesome. Awesome, right? Okay, so that's a question, and the answer is just as I believe many of you wrote, and many of you know, and I don't want. It is like, whoops, sorry, well, that's a weird one. It is like negative 0.15, like it's 15 centimeters on the other side of 0, as you'd expect. Why are we even bothering to, and this does assume that there's no friction in this spring, right? Oh, not because we don't believe that there's friction in the world, and not even because, by the way, not because physicists can't deal with friction. Physicists can deal with springs, and they can deal with friction. And if they want to deal with a frictional spring, then they put the both together. But they have to put both elements together. So right now we're looking at the element of spring without the element of friction. And we're believing that, right, in the ideal case, it would go all the way the same distance on the other side, as most of you wrote down. But quick note also, even if just in your mind, you just intuitively, like, okay. Sorry, someone's here. This is a rhetorical thing I'm writing right now. I'm not actually trying to challenge you at the moment. I just want to make a point. Like, I'm suspecting that I in fact know for a fact that most of you got this one right. And if I demanded that you show your work or justify it to me, a lot of you would be tongue-tied because it's like so obvious seeming. It'd be hard to sort of give a reason for why it's right. You'd be like, well, because it goes the same, right? And you'd be right to just have this sort of sense that should be true. But the sense, the intuition that you're having that this should be true, this intuition, the intuition is, and I know someone's in the waiting room. Sorry, I'll get it once people start texting it. It's a shock. Well, okay. When your brain says, I bet it's just the same on the other side, And then maybe even your brain then checks again and goes like, well, is that really realistic? Well, I guess it is if there's no friction. What your brain is saying is like, I think it's symmetric. I think there's some sameness going on here. Like it should be the same amount on the other side. And the thing is, that is not just like a raw gut intuition. That's actually quite rigorously correct. Like I want to highlight that any gut sense from here on in, when we're talking about this spring going back and forth, anytime you have a gut sense that there's some kind of symmetry operating, some kind of basic pattern where you could make predictions without even doing a bunch of math, in this case, you should trust that intuition because there very much is a symmetry going on here, assuming there's no friction. And the reason we're asking these questions in English right now, right after you did 2 energy conservation questions, is because we want to point out before going any further that actually, strictly speaking, energy conservation is what shows that symmetry. In other words, I'm saying, number one, if you wanted to show this thing mathematically, you totally could, because what we're saying is, just like in the above 2, now nobody would do this in their homework, and I understand that. I'm being a teacher, like showing you something that's going on in our brains. I wouldn't, but I know it's like, that you don't think of it this way, but right, strictly speaking, we're saying, we're noticing, when the thing's position is 0.15 meters, its velocity is 0. We're looking for what's the other place that we would ever find this thing where the velocity is also 0, right? And so if we say that energy is conserved, if energy is conserved for this, which we've been saying for the last 3 questions, that means the total amount of energy over any one spot at any one spot is the same as the total amount of energy at any other spot. And the 2 spots that we're comparing here for this question, again, I'm dragging this out on purpose for a reason to show something. The 2 spots that we're comparing here are the spot of 15 centimeters where we know for a fact the thing has speed 0 versus some other spot that we're looking for where we believe where the condition is that the speed also must be 0. So we're looking for the 2 spots are both when the kinetic energy is 0. Therefore, we're talking about the 2 spots where the potential energy must be the same, right? Like we're saying, duh. And this crosses out, and this crosses out, this way. So we're looking at the 2 spots. We're looking at 2 spots such that in both cases, x squared has to be, 0.0225, and it has a positive root and a negative root. And so that's therefore the answers are 0.15. And so the answers are, and of course, this. But I'm just trying to show right here that you can show that it's the conservation of energy is what is ensuring that symmetry that's in your mind. And in fact, that is a rule for all time, I want to say now. I want to say, therefore, like you didn't have to write this for your homework to prove your point, but one could have written it and it'd be correct. In other words, the thing goes to the same distance on the other side because energy is conserved. And I'm going to say, and this is always going to be true, that we're going to take advantage of symmetry a lot in this problem. We're going to, if you think you sort of shortcutted this one by saying like, I just got in my gut, I just know it's the same answer, -15. I'm trying to say here now, that's real physics. If you trusted your gut on that, it's not always true to trust your gut that like of sameness, but any system that conserves energy, any system that is governed only by a conservative force, what it actually means to conserve energy is to remain symmetric or the same with respect to time. And I mean this, in other words, homogeneity is not just a synonym for symmetry. Homogeneity is a particular kind of symmetry. Okay. Wait, sorry, hold on one second. Well, okay, yeah. Okay, I'm about to go on a slight like English. This is a slight metaphysical point about definitions in physics. Like it's not mathy for a moment, but bear with me if you don't mind for a moment. Like there's different ways that things can demonstrate sameness. When we're trying to pin down what space and time actually are or what they're like, there's everybody knows what space is in a way, and everybody knows what time is in a way, but we also all know that we don't really know what either one of them are. We just know they're there when we know what we're talking about when we talk about them. In fact, the ways in which space is both knowable and yet confusing at the same time are very similar to the ways in which time is knowable yet confusing at the same time. That is, both space and time seem to sort of be everywhere or infinite or something. Both of them seem to be sort of continuous. Like you can keep chopping up space smaller and smaller and you never get to grains of space, and you can keep chopping up time and you never get to grains of time. They both seem smooth, like, and everywhere, whatever that means. But yet there's something different about them. So what is, like, what's the relationship? Well, one way of thinking about space and time in English is space, whatever space is, I don't know exactly, but I know one thing about space. Whatever space is over here is what space is over there. Like this is space and that is space. This is not any more space than this is space or something like that. Put more specifically, like all of space is the same as itself. It's not necessarily the same as anything else, but whatever space is between planets is the same thing as what we mean by space between electrons or something. Very specifically, what I mean to say is space is symmetric in a way that we call homogeneous, like milk is homogeneous or homogenized. What we literally, that's not the only way that something can be the same everywhere, but what we mean by homogeneous, when we say that space is homogeneous, we literally mean that if you take a cubic meter of space from over like here, from my room. Okay, and you just imagine or picture or observe a cubic meter of space from over here. Now, not the stuff in it, but the space, right? Just imagine a cubic meter of space from over here. Now, also in your mind, imagine a cubic meter of space somewhere in Liverpool, England, or something, or like in your own apartment or something, some other cubic of meter of space, or a cubic meter of space in the Andromeda galaxy. The thing is that there's no, if you held those both in your mind and like sort of presented them to me or took a movie of both, there's no way I could tell the difference between the two. There's no way to distinguish a cubic meter of space from over here from a cubic meter of space from over there. Like that's kind of even what we mean by space, that it's the same stuff everywhere, whatever, or it's the same absence of stuff everywhere, right? Two equally sized regions of space cannot be distinguished from each other. That's what it means to say that space is homogeneous. Now I'm going to keep going for a second. Again, bear with me. This, I promise you, this is about the homework sheet, but space is homogeneous. The thing is, space also demonstrates a different type of sameness. Like one type of sameness demonstrated by space is homogeneity. It is homogeneous, meaning two equally sized regions of space cannot be distinguished from each other. On top of that, however, like next page, space is also isotropic. This is another kind of sameness. It's a different kind of sameness from homogeneity. Isotropic means okay, now this is subtle. Like, so this means, this is also true of space, but it's a different property of space, that in space itself, there's no difference between the x-axis and the y-axis, or north versus south, or left versus right, like on or up versus down. Like, and I'm saying space now, I mean space itself. So sometimes that's easiest to picture deep outer space, if you like on planet Earth, for sure, there's a difference between down and up, because planet Earth creates a gravity which pulls things in a particular direction, which we call down, right? But that's due to Earth. Just like, you know, when I say the two chunks of space, cubic meter, can't be distinguished from each other, I don't mean the stuff within space, I mean space itself. So same thing here. Space itself does not, there's no actual north in deep outer space. There's no actual down. There's no X or Y. Those are just our decisions, right? Space does not know the difference between forward and backwards. Like, I mean, there is a difference, but one of them is not designated forwards by God or something like that, right? So chunk regions of space cannot be distinguished from each other. No, there's no law that says this is right. And similarly now, or also directions cannot be distinguished in space. Space is homogeneous and isotropic. Why I'm saying all of this, well, there's a lot of reasons I'm saying, but one thing is to contrast it now with time. Time, well, I guess I'll ask you. So I'm going to compare and contrast now. And again, I'm off the sheet for a moment. I mean, you know what I'm saying? Like, this is not going to, and I think I just lost all of you. Hold on, sorry. Okay, I'm going, let me look at the, sorry. Oh, and where's the, sorry, the sun's right in my eyes. Wait. Cool. Okay. I like what Mr. Zhang said. That's cool. But now, Andre, great question. Where did the 0.0225 come from? Sorry, that's meant to be 0.15 squared. And why I say, sorry, good question. I don't know how long ago I missed that. Wait. It's because it's 0.0225 meant this squared, if that helps. I don't know if, and maybe I did that wrong in my head, actually. Wait, is that not true? Is 0.15, maybe it's not even true. No, it is true. Okay, but does that answer, Andre? Well, I'll assume it does unless told otherwise. But okay. So, but I'm going to ask you guys now. Oh, okay, great. Thank you. Thank you for saying that. I totally love that. Y'all, have I made that clear? Like, that's like, I should put, that should be a 50-point thing, or like a, you know, follow through with conversation, 75 points. I'll do one of those when I remember. Or I'll ask Tom Nook if I can. Space is homogeneous and isotropic. Let me ask you guys now. Think about it for a second. Time. Let's start with is time. And I'm actually asking you. This is a yes or no question. Like, I could take a vote or whatever if I want to put people on the spot. Like, there's definitely an answer to this. It's either yes or no, but it's based on the. It's not an opinion though. It's like based on the definitions I'm giving here. Would you say? Does it seem to you guys? Anybody can answer if they want, chat or whatever. I'm asking. Do you think time, by these definitions, is time homogeneous, which means two equally sized regions of time, can they be distinguished from each other? Space, the answer is no, they can't. So space is homogeneous. I'm asking you if anybody wants to take a stab at this. Time, by these definitions, would you say that time is homogeneous? That's awesome. Okay, I was just about to, yeah, cool, Aaron. Thank you. Wait, I'm just now typing the question for anyways. I'm going to say, okay, this is a question I'm at. Okay, cool. Okay, so first of all, Aaron, thank you for totally answering. I totally gets credit for having, whether she's right or wrong, I'm pretty confident that she understands the question. Same thing with Erica and Yabo. Thank you. I do want to say whether they're right or wrong. I don't want to dwell on this forever, but does anybody want to weigh it? Like, 3 people have said yes. Is there anybody that might have the guts or the interest in possibly conjecturing no? Or are we, I mean, I'm not trying to trick anybody, but well, all right, I guess, yeah, I guess this isn't worth. I totally appreciate that 3 people gave an answer. Wait, can I just get an electronic thumb or whatever from everybody? If you hear the question, do you know what question is on the table? Like, you don't have to give me an answer, but is everybody with? Okay, cool. That's fast. I love it. God, I wish this was a game show and you could all get money for that. Wait, no, I want the money. I'm sorry. Who gets the car? I get the car. Why do you get the car? The question is moot. That is a Saturday Night Live routine that starred Jesse Jackson, for anybody who watched that stuff. The answer is yes. I totally agree with everybody that wrote yes, yes. Time is homogeneous, and here's good. Maybe I should have asked them why, but they are right to say yes. Time is homogeneous by this definition, and you're going to see. Hopefully, this is about to get maybe almost interesting. Time is homogeneous, meaning if I consider like a minute of time, and remember, time and space are intervals, right? Like, time is the interval between 2 events that can be measured with a clock, and space is the interval between 2 events that can be measured with a ruler. So if I think of time, like I think of like 75 minutes of time taken out of, excerpted in my mind or examined in my mind, the 75 minutes of time on today, February 9th, whatever, from 12 o'clock in the afternoon to 1:30, like that 75 chunk interval of time. Now, if I consider that time, I don't consider what it's filled with. Just like with space, I'm not considering matter. I'm just considering the space between matter. Similarly with time, if I just consider the moments, not the events or the happenings that are occurring within, but if I just consider the moments of time that elapse in the 75 minutes, like during our class, there's no way to distinguish those moments from the 75 minutes that occurred, like when Jesus walked across to Galilee, blah, blah, like 2000 years ago. 75 minutes is 75 minutes whenever you look at it. That's why we call them minutes. Like, that's why we trust our measurements. Time is all intervals of time that are the same size have nothing else to distinguish them. There's no marks on this hour versus that hour. If it's an hour, they're all the same, right? That's the nature of time. In that sense, it's just like space. Whatever time is, it is the same over then as it is over yesterday. But now, why are we saying all this? Because note, you might see where this is going already. Like time, if I ask the other question now, remember, homogeneity means, wait, what? Wait, I gotta see. God, I wish I could read this. All right, I'm gonna look at it. I see things are happening in the chat. For some reason, I'm already laughing, even though I can't read them. But just to be clear where we are, I'm now giving two different types of symmetry, defining them: homogeneity and isotropy. Space has homogeneity and it has isotropy. No two equally sized regions of space can be distinguished from each other, and no two directions in space can be distinguished from each other. There ain't no difference between up or down in raw space. Now in time, no two equally sized regions of time can be distinguished from each other. Hence, time is homogeneous, just like space is. But now if I ask, before I read the, I'm going to ask, or I am asking, is time isotropic? And we look at the chat. My God, sorry, hold on. I look in the chat. Time, oh, okay, that is yes. I do get money from this. What? All right, I gotta hear more about how he gets money from this. But cool. According to our, oh, so I wrote that. Then you're saying time is a social construct. Sure, fine. Okay, fair enough. So are electrons for that matter. But is it? Oh, that's actually interesting. Yabo, I see what you're going with that. That's the Earth is spinning slower and slower. Yes, I can't deny that. And in fact, it is true that many years, you all know that like every 4 years there's a leap day. Like you all know that every 4 years we add an extra day to February and that's because it doesn't actually take 365 days to go around the Earth. It takes more like 365.25 days, although it's really like 0.248 or something, but it takes closer to like 365 and a quarter days to go around. Therefore, every 4 years we add an extra day to compensate, right? But similarly, what many of you might not know, that's also true, is many years actually we have a leap second. This is true. And this has to do with what Yabo was saying, just like a weird side note in a side note. Many, many years, the last minute of December, of the last hour of December 31st, actually technically, scientifically has 61 seconds in order to compensate for this effect that Yabo was talking about, which is that, yes, we are due to tidal friction slowing down. But that's so time is weird. Certainly time is weird, or our measurements are weird. But time itself, ultimate point I'm saying here is, GI Bill. Oh my God. Oh, no way. You're on the GI Bill. Good for you. Oh my God. I have to hear about that more later. Wow. Good for you. And by the way, thank you for saving my life in advance because I certainly can't save my own life. But I don't know if Marissa's, and I still a little bit, the whole woke thing is a little bit new to me too. But what I'm asking all of you is time isotropic? Because I'm at, maybe your answer's in the chat, but okay, cool. And I appreciate the guts and answering. I see that some of you are answering with thumbs up, but actually just to hold everybody's attention, I have to say, no, this is all why I think this is interesting. If you think about it for a minute, this is exactly where space and time are sort of like the same as each other, and yet sort of like not at all. This space is homogeneous and isotropic. If you think about it for a minute, what time is homogeneous, but not isotropic. The difference between time and space is that any two equally sized regions of time are indistinguishable from each other. Yes, just like with space, that's called homogeneity. But any two directions in time are distinguishable from each other. Time knows the difference between forward and backwards, at least so far as everything we ever experience or can so far discern in our physical experiences or our physics experiences. Right. So I'm agreeing with, I said, no, it's not. Yeah, with Sarah. And I'm not trying to trip you guys up, but I'm trying to point out, actually, this is a kind of an interesting English way to start getting at what's weird about the relationship between time and space. Like often we're going to treat time, often we do on graphs and stuff, treat time like just another axis, the way we have one or two or three axes of space, and then we have an axis of time. And we treat all the measurements similarly, like x minus x naught is displacement, t minus t naught is time, put one over the other, you got average velocity, yada, yada. But think about it for a minute. The difference between time and space is simply that in time, there is a difference between forwards and back, or seems to be experimentally, data-wise, observationally, experientially. Space does not automatically move you north or automatically move you south or anything like that. But time, flows in one direction, not the other. Time is not isotropic. Space is homogeneous and isotropic. Time is homogeneous and not isotropic, or technically the word is anisotropic. So this is just English, but I just want to lay this down, and you'll see, and bring it back to the sheet now. And if I'm not making sense, please let me know. But if you don't see why this is relevant, that I could understand. But just, do you see what I'm saying? Is the first question. In contrast to space, time. Now, why am I bringing all this up? Like, time flows. Time flow. I don't know what that really means. I mean, I have a better idea of it than I'm letting on right now. But of course, at the end of the day, I don't exactly know why or what it means to say that, like, you can sit still in space, but you can't sit still in time, right? Like, time seems to have this property where forward is different from backwards. And what's an example of that? Like, you put a cup of coffee on the table and steam rises. You've heard this a million times in chemistry class or something, but you put a cup of coffee down on the table and steam will rise off from that cup. Heat will move out of the cup, like into the surrounding environment. Steam will spread out, up and out from the cup. That's like a natural process that just happens with nobody doing anything about it. So much so that if you take a movie of that, oh, sorry. Oh, cool. Wait a second. Oh yeah, no, and I do. Wait, yeah, very fair question. And by the way, believe me, we can talk about the Big Bang and stuff like that. I totally would like to go there to the extent that we can. I mean, not literally go there, but I am talking here about, like, what so far thus seems to be accessible or observable in physics thus far. It's true. There are things I don't know, and I don't know what I don't know. And I'm not actually claiming that at the deep, deep root underneath it all, or in the house of God or whatever, that time, it's totally plausible that time is only coming across this way to us, but isn't actually this way. By the way, secretly in my heart, I believe that. Just for the record, like, I actually do believe time travel and stuff like that is possible if we really want to talk about it. I mean, but those details are not nearly as surfacely evident as as how difficult it is to travel in time, right? Like, at this point in our understanding of physics, there's something about directions in time that are harder to crack than directions in space. Let me be very specific now before I get too departed from the class. But everybody bear with me. This is now going to bring us back to question 6 and the energy conservation and the math and all that. If you put, and I know that everybody's heard this example in a way, but you might not actually have ever heard it in this context. Here's what I'm saying. Put a cup of coffee on the table while steam is, like, rising out of it. Let's say it's a lot of steam, like you can even see the steam with your eyes, right? Take a movie of that cup of coffee, like, make a video of it with your phone or whatever. Okay, fine. And now, like, walk up to your friend the next day, or to me the next day, and say, hey, I've got this movie of this thing that, right, we don't know. I'm just reading it. Right. Sorry, I'm just reading the chat. But, oh, is that why the answer is the same? Yes, to Anne Andre. Yes, and yeah, but okay, I think I've addressed this. But now take a movie of this cup of coffee with steam rising up from it, and then walk up to me or a friend of yours or whatever and say, I'm going to show you this movie of something I just made. Like, I just filmed something that happened. Like, and it's not a trick. It's like something in a natural phenomenon occurred, and I took a movie of it. Now I'm going to play you that movie. But you say to me, but, like, I might play it for you the proper way that I took it, or I might be like tricky and play it backwards. And I want you to tell me, even though you weren't there in the first place, I want you to tell me. I'm not asking you guys a class. I'm presenting a scenario. That imagine that you say to me, I'm going to show you this movie, but I'm not going to tell you in advance whether I'm showing it forwards or backwards. I want you to guess or tell me whether I'm actually showing you the movie backwards or forwards. And here's the deal. Again, I'm not asking you, I'm just asking you to consider this. If you did that to me, if you took a movie of a cup of coffee with steam rising out of it, and then you came up to me and you're like, now tell me if this is what really happened or not. if you played the movie for me forwards, I'd probably be like, yeah, I don't even understand what the question is. Like, this doesn't seem, yeah, a cup of coffee, steam rising out. Thank you. What's fun about that? But if you did play it backwards for me, if you played the video backwards, what I would see, right, is I would see a cup of coffee with steam like being sucked into it, right? Like the steam becoming less and less messy and funneling its way into the coffee. And if you had promised me that you weren't tricking me or anything, like you actually did take a proper movie or something that happened in reality, but now you might or might not be playing it backwards. If you played it backwards for me, I would freaking know that, right? Because in the natural world, steam doesn't just like direct itself into a little hole in the top of a cup of coffee. In the world, the way time flows is things spread out and heat rises. It's right. So if I saw that movie played backwards, I would know you played the movie backwards and if there's no tricks. Why am I saying all of this? Because let's turn back to the mass on the spring thing before I lose everybody. With the mass on the spring thing, think about this now. In our mass on the spring system, we've got something going back and forth naturally. Like we held it, we let it go. I mean, it's a really, really good spring, but we pulled the mass all the way out here and we let it go. And now we're just watching, just like you can heat up coffee and then let it go. So we let the spring mass go. And now it's going right for a while, and we film that. What I want to say very clearly, again, like everything in physics, this may sort of seem obvious, but it's not obvious that it's important. If you played that movie of wah, 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 back and forth, right, I'd be like, okay, that seems reasonable. I could imagine a mass going back and forth, like if it was a really long spring, and or just like I could imagine like a pendulum, for example, going back and forth and back and forth. And if you played it to me, I'd be like, that seems reasonable. And if you played it backwards, right, I would still see back, forth, back, forth. It would still seem totally reasonable. Now, wait, let me go a step further, because you might be saying, well, this is a trick example because you've got back and forth in there. So of course, but wait now, like, let's even say you excerpt it apart. Like, even if you just showed me this part, or you showed me that part, let's go a step further. Let's even say that you showed me a movie with numbers in it. Like you actually had the movie spit out measurements of exactly like every second where the mass was and maybe what its velocity was or something like that. If you think about it, whether you play the movie forwards or backwards for any segment, whether it was time that the mass was going like this or going like this, the whole movie is a mirror image of itself. Like that's what you're guessing in question 6, guessing correctly. What you're saying in question 6 is, I believe this whole thing is like such a mirror image of itself that actually, if I took a movie of it, whether I played the movie backwards or forwards, no one would be able to tell the difference, because this whole thing is the same backwards and forwards, even to the point, like just like anything with gravity, anything operating only under the conservative force of gravity would also pass this test. I want to be really specific now. I know I'm like yelling at the top of my lungs, but like, forget the spring for a minute, go back to our other friendly conservative force called gravity. Imagine throwing a ball up, and so that goes up to a peak height, and then it naturally comes back down. Like imagine that round trip, right? Which is like analogous to the mass spring round trip. If you imagine a round trip of ball going up and then falling down, what I do think most people would agree with is take that movie. I don't care whether you show that movie forwards or backwards, it's going to look the same either way. But here's the real thing. Like really, if you put the numbers in, it's going to be the same thing back and forth. And it's not because it's a round trip. It's not because it's a round trip. Like I'm not cheating. The round trip makes it more vivid to see. But here's what the real symmetry is that if you throw a ball up and then it comes down, on the way up, it has lower and lower velocities. Like as the positions get higher and higher, the speeds get lower and lower in magnitude. And then as the ball's falling, as the positions get bigger and bigger numbers or whatever, as the positions get smaller and smaller, the speeds get bigger and bigger. I'm saying whether you show me the up part or the down part, either one is natural. Like a ball going up is not unnatural or impossible. It's totally plausible to see a movie of a ball that's going up and know that it was a real movie, that you weren't tricked, as long as what you see in the movie is a ball that's moving up slower and slower as it moves. Then that's just as reasonable and natural as a ball speeding up while it falls down. All events under gravity are time symmetric that way. Any object that's just acting under the influence of gravity, take the movie forward or take the movie backwards, you cannot tell the difference. It will be homogeneous. It will be symmetric in time. Gravity phenomena will be symmetric in time. Spring mass systems, the ones we care about right now, will be symmetric in time, but not because everything in life is. Like what I'm really trying to say, and then we're going to move on, is if you had some just basic gut feeling, like I think the numbers are going to be the same. And if for the next question, question 7, I think it is, when I ask like how many trips will the thing make back and forth, if you're like infinity, it'll just go on forever. Yes, yes, yes. But your basic instinct that it'll go from 15 to -15 and go back and forth the same way forever. I now want to make it concrete and rigorous and real that what you're saying is true, definitively true, and you can rely on it because you're talking about a system that's conserving energy. It would not be true of a cup of coffee. It wouldn't be true of a car driving down the highway. If a car is driving down the highway, sure, a car can drive north and it can like speed up, or it could drive south and it can speed up, but it's going to have exhaust coming out of its pipe. Not to be technical, but there's going to be exhaust coming out of the pipe. And if you play the movie backwards, what you see is a car moving backwards with exhaust sucked into the pipe. Impossible. In other words, any system where there's heat output, any system that starts changing mechanical energy into thermal energy, once chemistry is involved or once other processes are involved, then we don't call that conservation of mechanical energy anymore. And what we don't have anymore is time symmetry. I'm saying, move on. I'm saying, oh, I guess I already did say, but I'm saying it again now. So any system, and only any system which conserves mechanical energy. I guess we did already write that, but I'm just now saying it again because hopefully it makes more sense now. Will demonstrate homogeneity. Will demonstrate I'm saying time itself is not isotropic. Time itself flows forward. It doesn't flow backwards. But systems that conserve energy jump themselves out of that restriction. Systems that conserve energy ignore or defy or somehow cut through the arrow of time. Systems that conserve energy drop the arrow of time and turn time into something completely symmetric. Any system that conserves energy demonstrates a symmetry of time. Any system that conserves energy means a system built from gravity or a system built from a spring force, or ultimately a system built from like an electrostatic force, which is where we're heading with this. That's yet another example of a conservative force. Any system built from a conservative force will demonstrate this kind of symmetry in time. And that is why any system that is built, any system that conserves energy, i.e. any system that's built from, say, a spring or something like it, is what we use in order to make or find in nature. I don't know where to write this. this mass on spring system that we're like analyzing to death, and I know we are, and we still haven't gone to question 9, and I know that, but all of this kind of background English and physics concept is to prepare us to do the actual math required for question 9, which is real math that we have to do in question 9. I'm kind of, taking a while to get there, because what I'm trying to build up here is the reason we care so much about a mass on a spring. I mean, like, really, what is the big deal? The big deal of a mass on a spring is that it is a representation of the pure, most elemental ingredient underlying anything that we ever call a clock, like a timekeeping device. What it means to measure time, to record time, to keep time, is to oscillate in a fashion that we ultimately call harmonic. Like, right, I haven't defined it yet, but I'm saying this mass on a spring is our first example of a system that is ultimately a clock, because it measures time, and you'll see what I mean by that. But you already do see partly what I mean by that. I mean, it certainly demonstrates something about time. It keeps time in a way, and the way in which it does that, we're about to call harmonic. I'll tell you what I mean by harmonic in a second. I will tell you right now. Okay, first of all, I mean, even though okay. And I will pause in a second. I mean, yeah, an oscillator. So I'm going to start calling this mass on spring system an example of a simple harmonic oscillator. Now, an oscillator is something that goes back and forth. I mean, casually, informally, an oscillator is something that goes back and forth, right? So if I go like this, I'm oscillating. Or if the amount of money in my bank account is going up and down, I could say it's oscillating. Those fans that sit on your desk and like swivel or back and forth are oscillating. So oscillating means, like, in a sense, back and forth. But what do we really mean? But it could be in a curve or in a line, or it could even not be in space. It could be like numbers on a graph. But what it really means to oscillate then is to move in a fashion that's somehow cyclical or periodic. Like, it's some kind of pattern thing where you end up doing the same kind of thing over and over. That's what we mean by there and back, right? There has to be a there and a back for it to be called oscillation. So oscillation means periodic, patterned, cyclical, there, back motion. But something can oscillate in a very spazzy way, like me. Like, I can, if I'm the professor in this, or I'm sorry, if I walk, I can walk back and forth in my room, back and forth, and I'm oscillating. But I could do it in a spazzy way. Like, I could start at position 5 and end up at position -4, and then I could go back over to position like +6, and I could go this way kind of fast, and then that way slow. So I'm going back and forth, but it might not be. For example, I might be doing cycles, like round trips, but I might take one amount of time to do one round trip, and then a little bit later take longer to do that round trip. So I'm oscillating, but kind of irregularly. To oscillate harmonically, as you can guess, as you can imagine, a harmonic oscillator, which is ultimately to say an energy conserver, harmonic oscillation, harmonic oscillator, I'm gonna have to go on to the next page. Sorry, this is important enough. I'm gonna rewrite this. So oscillator is back and forth motion. Oscillator is something moving back and forth. A harmonic oscillator, I'll write on the next page now. Sorry. Okay, we're almost back to this sheet and we're almost done with class, but I'm going to say now, mass spring system is a very symmetric system. Again, all of this is to say, at any given moment, if you have a basic instinct to think, I think like symmetry can help me solve this problem, you'd be right. I mean, you should follow that way of thinking, especially if you're thinking that somehow the oscillator is like symmetric in time, like whatever it does, that if it takes 2 seconds to do a whole there back thing, then it's fair to assume it takes 1 second to go there and 1 second to go back. And it's fair to assume that it'll take 2 seconds to do that again. Like you can assume these things about an energy conserver because they're true. And if they're doing that, then what we say is the system is not just oscillating. It's not just going back and forth. It's not just cycling. But in fact, if we're going to say it's harmonic, we're saying that it cycles at a rate which is constant in time. That's called frequency. And we're going to call that frequency. And the reciprocal of it is period. Like we're saying, if it takes 2 seconds to do a round trip, then it's always going to take 2 seconds to do a round trip. Or if we're saying it can do 2 round trips every second, then it's always going to do 2 round trips every second. It cycles at a constant. Again, not all oscillation is like that, but harmonic oscillation means oscillation, which is like that. And then the extra super special feature that will not seem special right now necessarily, but I want you to have it written down to have there for later is not only will a harmonic oscillator cycle at a rate which is constant, but that constant rate itself, it turns out, if something is harmonic, and this turns out to be very deep, that rate of cycling with respect to time is a rate that is totally independent of, unaffected by amplitude. And what do I mean by amplitude? Intuitively, I think you know, but let me just be rigorous about it. Amplitude from here on in equals maximum displacement from equilibrium. There's always an equilibrium involved because we're only talking about conservative forces here, and conservative forces always have equilibria. Amplitude equals maximum displacement. So just to say this, we're going to really, again, we're going to have to make use of this in lab. We're going to come back to this, but as a definition of harmonic oscillation, what I'm saying from here on in is it's oscillation, which is steady in time. It's cycling, which cycles at a constant rate. No tricks up my sleeve, just kind of what you'd expect. But I want to fix in your mind that if you think of from here on in amplitude as the farthest that a system is from equilibrium. So like in our case here, 15 centimeters would be the amplitude, right? Often that in fact is the initial displacement. Like if amplitude means the maximum displacement from equilibrium, then often that ends up meaning the same thing, being the same thing as initial displacement from equilibrium. Strictly speaking, by amplitude, we mean the farthest we ever get. Strictly speaking, that means the place we arrive at when our speed becomes zero, right? If you think about it, by an amplitude point, we mean a turning point. Whether we actually think it was officially the beginning of the experiment or not, it's the place where something loses all of its velocity and is about to start having velocities in the opposite direction, so turns around. In other words, an amplitude point is a turning point, if you like, for anything that's cyclical. Turning doesn't have to mean physically turn left in space, but it just means reversing a cycle. What a harmonic oscillator is one that oscillates at a rate in time which is completely independent of scope in space. It's a crazy idea that we're going to probe more, but if you're paying attention, if you're following me, I am saying now, well, I don't want to give it away, but I am saying that however amount of time, we're going to find out how much time it takes for this system to go from 15 centimeters to negative 15 centimeters back to 15. Like imagine we could figure out how much time that is. We're going to find it. I'm going to say what we're going to find is that that amount of time wouldn't change even if we had started this mass at 7 centimeters rather than 15, or even if we started the mass at 40 centimeters out here. Like even if we subjected this mass to swings that were much bigger or smaller in space, we're going to end up finding, due to energy conservation, that each swing will still take the same amount of time. What it means to be a harmonic oscillator is to demonstrate a constancy in time that can't be messed up even if you mess with things in space. Whether the mass goes back and forth like this or back and forth like this, somehow the times are going to work out the same. We're going to find, I'm sort of giving this away by saying this, but as long as I'm saying it, let me be super vivid, and we also might as well end on some kind of note. I'm literally saying that if I pull this mass out to 15 centimeters, we found by pulling it out to 15 centimeters and letting it go, we found that the mass raced in toward the center, and by the time it got to the center, achieved a speed of 3.87, like instantaneous speed of 3.87 approximately meters per second, right? And then it was slowing down until it got to 0. So on average, just for the record, that means it was like 0, faster, 3.87, slower, 0. So on average, this thing was going about 3.87 meters per second, right? So on average, it had a certain amount of kinetic energy. If you think about it, if we had started this mass at way far out here, it would have a much farther way to go to get to equilibrium, and then much farther go to the other side. So we're now asking it to make much bigger cycles, bigger in space, bigger swings. But if you think about it, if we started it way out here, it's going to start with a lot more potential energy. And by the time it gets to the center, it's going to have a lot more kinetic energy than our 15 centimeter spring did. Like it'll be going a lot faster than 3.87 if we start it way out here. So it turns out that bigger stretches, bigger amplitudes actually lead to bigger average speeds. That's already an interesting thing to note. And it turns out that the two effects perfectly compensate for each other somehow. The bigger distances yield bigger speeds, so that whether we start the thing at 15 centimeters or we start it way out at 60, if it goes wah or if it goes wah, each wah is going to be the same amount of time. And so each tick tock is a tick or a tock, no matter how we configure the system. It's why it's a clock. It's a timekeeper, because it's going to keep time in a way that's independent of space due to energy conservation. I know there's a lot of talk. Let me just try to, so quickly back to the sheet. I know we're not going to get to 9 today. I think we have 2 minutes. Let me, we did 6, I know I'm just talking, I'm not even looking at the chat, sorry, Alona. We did 6. So 6 was 57. So then 7, I don't know if I said this, but the answer is certainly infinity. It will do infinite number of cycles back and forth. Now 8, I'm going to do this quickly, but 8, remember I asked, 8 is the question where I say, all right, if we just look at that first 15 centimeters as the thing moves in from x equals x naught to x equals 0, right? If we just looked at that first chunk, I'm just looking at the time. I think we would like to bear with me for like 3 minutes. When we look at that, most of you said that the speed, like just the magnitude of velocity from the edge point to the equilibrium point, most of you said correctly that the speed is increasing, right? It's going from 0 to 3.87, just to establish, no trick, just want to make a point. It's going from 0 to 3.87, fine. But then the acceleration, the magnitude of the acceleration, most of you correctly noted for whatever reason, it was in your mind, as the mass goes from the edge point, the amplitude point in toward the center, although its speed is increasing, its rate of increase, its acceleration is in fact decreasing, right? Because way out here, there's a huge acceleration of 100 meters per second squared. Happens to be negative, but I don't care. We're asking you about magnitudes here. Like, yes, it's negative, but that just means it's that direction. Out here, there's a huge amount of acceleration, huge force, huge potential energy. And then it comes in, by the time it gets to the center, it's moving really fast, but it has no acceleration at all, right? X equals 0. So the acceleration is going down. Then I asked, what about what I'm calling the jerk? In other words, and this is where we're about to get to the calculus finally. We'll pick up with this next week. I know we don't have school Monday, Mazel, God bless. But like if speed is in effect this, or velocity is in effect this, and then if acceleration is in effect this, I'm now asking, even if we never used the word for it before, even if we never cared before in a physics class, I'm asking, could we speculate what the third derivative would be? And this is where we're going to sort of end for today, and we have to get to question 9. But if I'm going to ask you to speculate about what the jerk is doing, in a way, I'm asking you to, you don't know, I'm asking you to conjecture. How could you possibly even begin to conjecture? One quick way to at least conjecture is to back this whole process up and notice that even though I didn't ask, you could ask yourself, wait, when the position's going up and the acceleration is going down, what's happening? I'm sorry, when the speed is going up and the acceleration is going down, what's just happening to x itself? Like, in other words, we're looking at derivatives here. Let's go back to the original function for a second. And we're just going to end on this. I know it's just about 130, but when the mass is all the way at the beginning of this whole experiment, we call that position positive 0.15. Then where does it go? It goes to the equilibrium position of 0. It speeds up in that way. Yes, we said speeds up, but what's its positions doing? They're going down, right? As it moves down from 15 to 0, its speed goes up, but its acceleration goes down. I have three choices here. Like, this is a multiple choice question for jerk. Is the thing going up or down or remaining the same? I got three choices. I might not be sure of my choices, but I have, if I just look at this pattern, I can't prove that this pattern is always going to hold forever, but I might conjecture that if there's anything to this pattern, that what I have some reason to predict that the answer to jerk is it goes, if this pattern holds, presumably the next derivative goes up. The thing is, do I know for a fact that this pattern holds? If I believe everything I've just been saying, it's a lot, but if I believe that energy conservation really means constancy in time in this deep way that I'm trying to say, if I can really rely on the fact that energy conservation really means sameness, it means patterns are going to hold, that once they hold for a little while, why they're going to go to infinity. And this pattern does. I'm not saying that's a proof, and I'm not saying you should have known this. I'm saying a way to think about it now, that the answer to this one is up. And for question 9, we're going to solve it all together next class. But how can you even start question 9? This is where you start by saying, well, we know that this is true, and we know that this is true. So we're going to say, so we might, in this case, since there's only one force acting, this is where we're going to end today, just setting it up. We know that here in this case, negative kx equals ma. Now we're looking for like x as a function of, I mean, it's asking where will the thing be in 1 second? We're trying to figure out some equation for which if you plug in t, you get out x. We just remember definitions. The definition of instantaneous velocity is first derivative of position. The definition of instantaneous acceleration is derivative of that, right? Like derivative of derivative. In other words, second derivative of position with respect to time. So the one thing we know, and this is where we're ending, this is not an answer, this is how to set up and try to find what we know for question 9. We know, sorry, I'll write on the next page. And there's the last thing I'm writing. For question 9, what we know is we're ending. Like, we want x as a function of t. We want some rule where if you plug in 1 second, you get out the appropriate position. We have an equation here that only has variables x and t in it. Somehow this equation must be solvable for x and t, but we have to solve it. We're not there, but we have an equation here. Physics is giving us an equation for which there's a bunch of constants. Like, and you can plug in numbers for those constants for m and k and stuff, but the only variables in it are the variables we want, x and t. We just have to rearrange or unpack this equation somehow to get x as a function of t. That's what we're going to start doing on Monday. That's totally where we're done for right now. Sorry about all that. I'm going to stop for a sec. Like, if you want to go, please say goodbye and go. I'm going to just sit here for like a minute or two in case there's any questions or appointments or anything. But other than that, thank you very much. Sorry to keep you. You guys are awesome.
Thank you, Professor. Have a great weekend.
Thank you.
Thank you,
Yeah,
Professor. Bye.
yeah, have a great, thank you. Have a great long weekend. That's right. Thank you, Erica. Thank you. Yes. Awesome. Thank you. I will post this. Thank you. Bye. Thank you. Awesome. Thank you.